Hello maths fans, Dr. Tom Crawford here at the University of Oxford, and today I'm joined by a special guest. This is PK from the YouTube channel Dr. PK Math.
Hi everyone.
This is the second time that we have made a series of videos together. So a few years ago, PK got in touch and said, have you seen this crazy Korean exam question from the Korean SAT? It's a killer question. Let's try and solve it together. So we went through that. I still have nightmares about that problem. It was that difficult. And today we're going to be doing more difficult problems. But this time, they have not come from a specific exam. They have just come from the mind of PK himself. So the first part of this collaboration we filmed and is now available over on PK's channel. And in part one, PK introduced the topic. We're talking about determinants, but determinants of matrices that also involve integrals. So there's like a combination of algebra, calculus, all kinds of stuff coming together. We've gone through part one. It was kind of okay. I'm very glad we did not have to do the 7x7 determinant. And now I've been challenged with the second question. This is part two. Now, PK has already explained to me the question at the end of the video over on his channel, but for all of you watching, in case you haven't seen that yet, PK, would you like to introduce this hideous, horrible, terrifying question that you would like me to try and solve?
Okay, so the question I'm challenging to Dr. Tom is we should determine the determinant of this 2x2 matrix A, but A, this is an integral. Integral from 0 to infinity, then we have exponential function on the integrand. So e to the power of this capital letter M, but M is now 2x2 matrix, as you can see. So we have 4 elements, but all of them are quadratic function about the x. So your M is x squared minus x, 2x squared minus x over 2 minus x squared, x over 2 minus 2x squared. So Tom will be working on determining the determinant of this 2x2 matrix A that is represented as an integral.
I just love that the question that you worked through, PK, was a 7x7 determinant, which in theory looks terrifying, but as you showed us, could be done with some neat tricks. And then now this feels much easier. It's like, oh, it's only a 2x2 determinant. But as we can see, it is, you have a matrix M, you then take the exponential function, e to the power of that matrix. So first of all, I'm thinking we've got to make sense of what does that mean? What does that look like? Then I have to integrate the result, and then I have to take the determinant.
Much harder.
Now, before I get stuck in trying to solve for PK's determinant, I just wanted to address a very common question that I see on videos of this type when looking at a difficult exam-style problem. And that's about how to start one of these questions. So how do you even begin knowing where to look to begin to find a potential route into the problem? Now, the simple answer is it comes down to practice. Now, a lot of you probably already know this, even though you might not want to admit it, and that's because practice is hard. It takes a lot of time, it takes a lot of effort, and it takes a great degree of motivation. But one approach that I personally find really helpful when I want to focus on learning or improving a particular skill is to work with a tutor. And that's where today's sponsor, SuperProf, can help. Founded in 2013, SuperProf is the global leader in education. With millions of tutors across more than 50 countries, there's always something new for you to learn in over 2,000 subjects. Tutors are available in maths, physics, sports, guitar, pretty much anything you can think of. And with SuperProf, you're in charge. Sign up today using the link below and see what you can learn. Right, that's probably enough stalling. Let's see how I get on with PK's determinant problem. Okay, so step one here to me feels like we need to make sense of e to the power of a matrix, right? So we've been given this 2x2 matrix M, and at this point I don't really care too much about what that is. I just need to, like, what does it mean to take e to the power of a matrix, the exponential function to the power of a matrix? Now this is something I've spoken about this before in a couple of Numberphile videos, And actually, I also teach this to my students when we do quantum theory. So it's something I'm relatively familiar with. And again, anyone watching, you will see this kind of operator if you end up studying quantum. We often talk about exponentials of matrices or operators themselves. So I think let's start by saying, well, if I have e to the power of x, sort of the classic exponential function, then this can be written as a power series. So for, let's say, x is just a number, then it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And then we just kind of do this all the way to infinity. So this is our typical power series for the exponential function. So what we want to do here is actually just generalize this for a matrix. So if I have e to the power m, which interestingly by itself makes no sense because it's a number to the power of a matrix. Like, I honestly have no idea what that is, but we make sense of it using the power series. So we don't have a 1 when we talk about matrices, but we have the identity. So we would say this is equal to the identity matrix plus the x, which is now our matrix M, and then plus our matrix squared divided by 2 factorial plus our matrix cubed divided by 3 factorial, and then we carry on. So we still have an infinite sum. We still have an infinite series, which we'll worry about shortly. But the important thing is we know what the identity matrix is. We know our matrix M. It's this thing with polynomials. We can work out, if we have to, we can work out m squared, m cubed, and all of those powers of a matrix. You just multiply the matrix by itself and try and add them all together. Now, that of course is not how we're going to solve this, but it is how we're going to make sense of the exponential function. So the way we're actually going to solve it, and PK, you gave me a very helpful clue in part 1 when you mentioned diagonalization, because that here is really going to be key in allowing us to work out the powers of this matrix. So what we actually want to do is use this process of diagonalization on the matrix M. So what I mean by this is diagonalization. So we want to find two matrices, D, which will be a diagonal matrix, and then a matrix P, which is invertible, such that M is equal to P times D times P inverse. And D is a diagonal matrix. Now, at this stage, we don't know if this is possible. We'll worry about that shortly. But if we can do this, this is going to help us, because using this, we can then say, or we can simplify how we calculate powers of the matrix M. So, for example, if I wanted to work out M squared, which is the matrix M multiplied by itself, so that's P times D times P inverse, that's M, times P times D times P inverse. That is M multiplied by M. But of course, what we've got here is a P inverse multiplied by a P, which just gives us the identity matrix, which basically plays the role of 1. So this is where the simplification happens, because what this means is that M squared is P times D squared times P inverse. And now our matrix D, right, this is all good, but we need D squared has to be simpler than M squared, right? Otherwise, we haven't really done much. But because D is diagonal, so for example, D is going to look something like A0, 0B, then D squared, you multiply that by itself, you actually just get A squared 0, 0B squared. And so this is the key to actually simplifying the whole problem. Because whilst I've calculated this for D squared, the same thing, or M squared, the same thing is true here, actually, for any power of m. So I can go back and say, well, this actually is now just to the power n. You just have all of these multiplied by one another a total of n times. But at every bracket, the p and the p inverse cancel. So m to the power n is actually just p times d to the n times p inverse, and then d to the power n is just a to the n, b to the n. So what all of this means is now we can actually simplify over here our e to the m, our exponential matrix that we're trying to work out. So what have we got? We've got e to the m is equal to, now if I write this as a sum, just so I can use this m to the power n term, then it's the sum from n equals 0 to infinity. It's just shorthand for what I've written here, of m to the power n divided by n factorial. Now, the m to the n, we've said, is just p d to the n times p inverse. So I can substitute that in. So this is now the sum from 0 to infinity. I'm going to put the 1 over n factorial first, and then m to the power of n, remember, is now just p times d to the power n times p inverse. Now, this term in the middle contains the n, so it has to be included in the sum, but the p and the p inverse do not contain an n. So they can come outside of kind of the whole sum. You can like factor them out of the bracket, if you will. So this whole thing is now p, and then I've actually just got a big bracket, and inside here I've got the sum from 0 to infinity of, what's it going to look like? D to the n over n factorial times p inverse. So now we just have to make sense of d to the n. But again, as I showed over here with the squared, and then we generalized it, this is actually just the individual entries to the power n. So what this is all going to look like is I can actually just take the sum inside the matrix. So finally, this will be this matrix P. We haven't worked it out yet. We'll get there. Then we've got, in here, we've now got a matrix. So we've got the sum from 0 to infinity of whatever this entry is, which I called A, to the power n over n factorial, 0, 0, and then the sum from n equals 0 to infinity of b to the n over n factorial inside a matrix, which is wild, and then the p inverse finally over here. So I'm aware I did that quite quickly, but this question is going to take a while as it is. So if needed, if anyone watching, do go back and pause and try and follow along for yourselves. But hopefully what I've done is we substituted for m to the n using this diagonalization procedure. Again, we do still need to check that works. That's going to be stage 2. Then we factored out the p's, and then we realized because this is a diagonal matrix, when you take it to higher powers, you just take those entries to those powers, which allows you to move the sum inside the matrix. So, putting all of this together, what we can actually say, and I've kind of run out of space, but I'll write it here, is if we now do this sum, this is now just an exponential function. This is literally just e to the power of a, based on that initial definition. So we can say that e to the m, we've turned into p multiplied by e to the power a, 0, 0, e to the b, times p inverse. So let's kind of put a box around that. That's going to be important. That's a big P, like so. So now we have, I wouldn't say we've simplified, but we've made sense of what does e to the power of a matrix look like, what does it mean? We've found some way of representing it. Again, we still need to compute all of these things, but now we can actually try and use the definition of the matrix M, like those specific entries, and try and work out, well, what is P inverse, what are these values A and B. So now, in order to make progress in stage 2, I'm calling, of the solution, we need to work out what is this matrix P. Is this possible to construct or to diagonalize our matrix M? So we need to work out how do we construct P, and also what does our diagonal matrix D look like? What are these entries A and B? Now, PK, I think you might have some suggestions or some ideas about how we do this. So what are we going to have to do next now?
Okay, so an amazing work for you to work on diagonalization. So since you worked on diagonalization, now we need to find the P and D, like you said, right? So in order for you to find the P and D, then we should work on eigenvalues and eigenvectors, because your matrix D, which is 2 by 2 matrix, it should be like those two eigenvalues with the 0. So we should find 2 eigenvalues, then at the same time we should find like V1 and V2 in order for you to construct the P, which is also 2 by 2 matrix. And those V1 and V2, which are column matrices, should be your eigenvectors. So next step seems to be for you to work on eigenvalues and eigenvectors.
Exactly, thank you. So, just to write that up so I can keep track of what I'm trying to do, this diagonalization process, it's something that's well studied, it's well established in linear algebra, and it says that we have to find, first of all, our 2 eigenvalues, because M is a 2 by 2 matrix. So those 2 eigenvalues are actually going to be our entries A and B, and then the corresponding eigenvectors, which I'm calling V1 and V2, are going to form the columns of our matrix P. So I actually now need to use the form of the matrix M. So M is equal to x squared minus x, 2x squared minus x over 2 minus x squared, and x over 2 minus 2x squared. Okay, so in order to solve for the eigenvalues, we of course solve the characteristic polynomial, which says that 0 is equal to the determinant of m minus lambda times the identity. So I'm going to take away sort of lambda from this, so I get a minus lambda on this one, minus lambda on this, and then the determinant of that is going to mean I get x squared minus x minus lambda times that one with the minus lambda, and then minus those two multiplied together. So minus 2x squared minus x multiplied by x over 2 minus x squared. So this now gives us a quadratic equation in lambda. This will have 2 roots, and those 2 roots are going to be our eigenvalues. Now, I don't really want to go through all these steps. I'm sure everyone following, right, you should check this, make sure you can expand this out, and make sure you can actually find those solutions, right? It's a quadratic equation in lambda, remember? So lambda will be written in terms of x. But I believe, what eigenvalues should we get, PK? Did you figure this out?
The first one seems to be negative x squared.
Okay, so our factor would be lambda plus x squared. Yeah.
And then
the
second factor should be 2 lambda plus x, so it is negative x over 2.
Thank you very much. So again, for those of you watching, you should figure this out yourselves. I'm just using my cheat sheet of PK because I think we can all agree I know how to do this. I'm just saving a bit of time for us all. Right, so we've got our 2 eigenvalues now, haven't we? So we've got lambda is minus x squared, is going to be one of them. And then we've also got lambda is minus x over 2. Right, so let's call that lambda 1 and lambda 2. So now we have to work out the eigenvectors, of course, right? That was our how to work out our matrix P over here. So maybe I'll do one of these and then you can give me the answer for the other one. So let's solve for lambda 1. So I want to solve my matrix M, so I need x squared minus x times 2x squared minus x times x over 2 minus x squared times x over 2 minus 2x squared. I need that multiplied by, let's call it alpha beta, must be equal to minus x squared times alpha beta. So I'm just going to write that as minus alpha x squared and minus beta x squared. So my eigenvector will be alpha beta, and I now have to solve this. So the first row is going to tell me, what is it going to tell me? Alpha x squared minus alpha x plus 2 beta x squared minus beta x has to be minus alpha x squared. And then the second row tells me alpha x over 2 minus alpha x squared plus beta x over 2 minus 2 beta x squared has to be minus beta x squared. So looking at that top one, I can see I don't have a linear term. There's no x term over here. So that means that alpha plus beta must be 0 from that top one. And I'm going to, hopefully, that will be the same and be consistent throughout. But let's check. So I've got alpha plus 2 beta must be minus alpha. So alpha plus 2 beta must be minus alpha. That's to make the x squared term balance in this first equation. So this one and this one must balance with that one. But that's, of course, the same equation. That's 2 alpha plus beta equal to 0, so alpha plus beta is still 0. And I believe the second one is going to be consistent and going to be the same. So, for example, then, I could say v1 is just any pair of vectors, so let's do minus 1, 1. So I just need the sum of them to be 0. So let's just pick minus 1 and 1, nice and easy. And then, of course, I would solve something very similar for the second eigenvalue. So instead of x squared, I would substitute in the x over 2, and we would solve something similar. And what will we get that time, PK? I'm going to use you as my cheat sheet again.
Okay, so if you replace
What's
that...
our second one?
Yeah, the second eigenvector should be negative 2, 1.
Negative 2, 1. Perfect. Thank you very much. So again, anyone watching, you can just solve exactly as I've done here to find that eigenvector for yourself. Okay, so now we have our eigenvectors. This gives us P. So, where am I going to write this? Let's put P over here. So I just put the first vector in that first column. This is going to be minus 1, 1. And then the second eigenvector in the second column, minus 2, 1. And then we can work out P inverse. So the determinant of P is just minus 1 plus 2 is just 1. Makes it nice and easy. So 1 over the determinant is just 1 over 1. So I'll just write that. And then for a 2 by 2 inverse, you swap those two. So I think that's 1 minus 1, and then you make the other two opposite signs. So I think it's that, I think, is going to be P inverse. So I've got P and P inverse over here, ready to go. We've got our matrix D, and we've got A is equal to minus x squared, and B is equal to minus x over 2. We've got D, A and B ready to go. So all of those now get substituted in up here, and finally, we can move on to stage 3 of who knows how many stages in trying to solve this problem. We're going to now actually try and compute this matrix and hopefully do the integral and then finally do the determinant. There are so many steps to this problem, but I'm loving it so far. Now on to the third stage of the solution, which is hopefully the final one, but we'll see. We have started by making sense. So we use diagonalization. I think I'll write that back up because it's such an important concept that actually allowed us to make any kind of progress with this problem. So we use diagonalization in the exponential function to make sense of e to the power m. And we figured out that we just needed to calculate a, b, p, and p inverse. PK very helpfully suggested that we can do this using the eigenvalues and the eigenvectors, which I've just computed, and then we worked out P inverse by just inverting a 2 by 2 matrix. So I now need to just expand this out, and hopefully we'll be left with a final matrix, he says. So of course, we just have 3 2 by 2 matrices, so we would just multiply this out to get our final 2 by 2 matrix. I'm feeling lazy. This is already a very long solution, so I just cheated and put this into a nice computational engine that gave me this. So I believe this is going to come out now as 2 e to the minus x over 2 minus e to the minus x squared. The next one is going to be 2 e to the minus x over 2 minus 2 e to the minus x squared. And then our second row, e to the minus x squared minus e to the minus x over 2. And finally, 2 e to the minus x squared minus e to the minus x over 2. So we made sense of e to the power of a matrix through diagonalization, and it turns into this 2 by 2 matrix. So I think finally we can actually now get stuck into the problem. So it's been a while, but I think I have to integrate this, PK, is that correct?
Yes, all looking all good.
Okay, so I think it was, we said the matrix A was equal to, it was 0 to infinity of e to the m dx. Right, so we now, not only do we have a matrix involving exponentials, we now have to integrate this. So the way this is going to work is we actually need to integrate these 4 components individually. And the way I'm going to think about this is by actually spotting or identifying that really we just have 2 separate terms that we need to integrate. So there are numbers and things floating around, but fundamentally, right, I've got to do 4 separate integrals. Rather than writing them all out, it's actually just broken down into integral 1, which is going to be the integral from 0 to infinity of this term, e to the minus x over 2. So if I know what that's equal to, I can just substitute that in. And then I need to know integral 2, which is going to be the slightly more complicated one, which is going to be 0 to infinity e to the minus x squared dx. Now, the first one, reasonably straightforward. This is actually just going to be like a reverse chain rule, if you like that language. But this has just come directly from minus 2, I think, e to the minus x over 2. 0 to infinity. Let me just check that. If I differentiate that, I bring down a minus a half, which just turns it into a 1 as my coefficient. So now when I substitute in infinity, it's e to the minus infinity, which is 0. Really, I should take a limit here. We won't worry about it. We can just imagine substituting it in. So it's 0 minus 2 times e to the 0. So that just gives me 2, because e to the 0 is, of course, 1. So this integral is actually just 2, which is nice and straightforward. This integral, we can't do. At least you can't do it directly because we want to use reverse chain rule, but we've got an x squared, we need an x here, and we don't have it. So this is actually a famous integral here. So how would you do this, PK? How would you refer to this function?
Gaussian integral, working on it.
Okay, so you'd call it the Gaussian. Okay, yeah, because I believe some people will call this the error function,
right,
as well, and talk about, yeah, it's something that comes up so often. It has many names, and we use it in different contexts. So yeah, I'm with you. I would call it a Gaussian. It looks like the normal distribution. If any of you watching have seen the normal distribution before, you can actually use that to deduce the value of this. But again, not that I'm trying to push Numberphile, but again, I made a recent Numberphile video where I explained how to actually compute this. We called it the Big Daddy integral because it's such an important integral. So I showed how to compute this, and this is actually equal to, really nice result, it's the square root of pi divided by 2. So again, this is kind of just like a known result. It's a whole other video to explain where this has come from, so I'm just going to state it at this point. But now I think I can substitute all of this in to my equation. And when I say substitute in, what I probably should have emphasized here is I'm doing the integral of this, which means doing these 4 separate integrals. So this is kind of what I'm doing. So plugging all of this in, I can now say that A is, so we've got 2 multiplied by this integral. So that's 2 times 2 gives me 4. And then I'm subtracting off this integral. So it's minus root pi over 2. Next term, I've got 2 times 2 again, so that's 4. And then I'm subtracting off 2 lots of this one, so that's minus root pi. This one, I've got e to the x minus x squared, so that's a root pi over 2, minus 2. And then finally, 2 lots of that, so that's a root pi, minus 2. Yes. Okay, so now it looks like something I can actually calculate, thankfully. So I think the final step, and I'm sure you'll correct me if I'm wrong, PK, but I think the final step was the determinant of A.
Yes.
There we go. All right, we got there, everybody. We got there. Stage 3 was the final stage, thankfully.
Wrongly.
Right, so the determinant of A, this is the easy part. All of this work just to get a 2 by 2 determinant. Right, so it's just that one times that one. Let's write it out properly. Let's not make a mistake at this stage. 4 minus root pi over 2 times root pi minus 2. Subtract off the other 2, which is root pi over 2 minus 2 multiplied by 4 minus root pi. Okay, right. So expanding that out, what am I going to get? 4 lots of root pi minus 8 minus pi over 2 and then plus root pi. And then we're going to take away 2 root pi from that one, minus pi over 2, minus 8, and then plus 2 root pi. So I have a feeling there's going to be some cancellation. So we've got a 4 root pi minus those lot, minus 8 plus 8, minus pi over 2 plus pi over 2. There you go. Which means it's just that. No way. Is the answer just root pi? Okay, I think the determinant is root pi. That is if that is correct, that is an amazing answer.
That's all correct. It's all beautiful work.
Woo! Okay, that was awesome. I love that is the answer. I had no idea the answer was going to be root pi. That's amazing. Wow. So so what did we do? We did e to the power of a matrix. We made sense of that. We used diagonalization, turn it into this thing. Then we integrated and used the Gaussian or the error function. And then finally, we got our matrix A, compute the determinant, and it's root pi. That is magic. I love that. What a question. I feel like I've just taught an entire undergraduate course of mathematics in just trying to explain that answer. You weren't kidding when you said it was a difficult but interesting problem, PK. So thank you so much for sharing. That was awesome. I loved it.
Yeah, at least the result turns out to be really nice. Square root of pi. So.
It does. It does. Yeah. Brilliant. Well, that was a lot of fun. So thank you, PK, for sharing the question. Thank you, everyone, for watching. I hope you enjoyed that as much as I did. As you can see, I've got a giant smile on my face. That was genuinely brilliant. I love that the answer was root pi. I love all of those steps that we had to go through. There was linear algebra, there was calculus, there was exponential series, power series, which is like analysis. It's all kinds of really cool math techniques in there. And just as a reminder, this was part 2. This was the tricky problem we did earlier, or PK, I should say, earlier, did solve part 1, a 7x7 determinant question involving integrals. So if you haven't seen that yet, go check out part 1 over on PK's channel. Check out all the other brilliant maths videos over on Dr. PK Math. And again, PK, thank you so much.
Thanks for having me, Tom. Thank you.
My pleasure. And no doubt you will send me more horrible questions to solve in the future.
For sure,
Because I love it, right? I keep saying horrible. I clearly love this. Please do remember to subscribe to the channel if you've enjoyed this, and check out all the other content on the channel, including that earlier Korean SAT exam question that I solved with PK a few years ago. I will be back very soon with some more maths. Take care. And before you go, don't forget to check out SuperProf for all your tutoring needs using the link in the video description. I'm in the mood for learning some philosophy, and Antonia looks like my new teacher.